Okay, so now we come to the real, the thing that we really want to talk about, which is many-body physics. So we made this excursion to single particle physics to see how functional methods in the form of the path integral can be used to arrive at an alternative formulation to quantum mechanics, which you already knew. It was done to get used a bit to this concept of path integrals, and also to already see like this flexibility to consider time as an imaginary or purely as a complex variable, which then allows to let's say quantum mechanics to statistics. So here now we really come to the coherent state field integral, and the concept that we use so far will be just like a bit generalized or applied in a different way. But what is appearing now in the next two lectures should be by now familiar to you. So, so as I said, so there will be, I think, two lectures on the construction of the coherent state field integral, which allows us then to address many-body problems, and this will be from then on done. So now we are back to many-body physics and consider again, like in the first lecture, I gave some examples for the typical Hamiltonians that we're interested in condensed matter physics. So let's consider a prototypical Hamiltonian that we encounter in condensed matter physics, a many-body Hamiltonian, so we have some interactions there. Now let's just write it down in the second quantized language. So we have a Hamilton operator that depends on operators A, and A, creation, annihilation operators, and like the typical form would be that you have some quadratic term which describes a non-interacting free problem, and then you have some quartic term which accounts for interactions between the particles. So now let's keep the discussion general. That is, let's consider A dagger, AE, bosonic or fermionic operators. Fermionic operators fulfilling corresponding algebras. So we have AJ. Now here I write plus minus for the commutator or anti-commutator, depending on whether you consider fermions or bosons. Let's just give my formula. So let's look at this kind of problem, which all of the problems that we will discuss later on will be just of this form. Okay. Then let me just introduce the number operator, which counts how many particles you have in the system. So let's just do A, it's a particle number. Particle number operator. So here I use some discrete index I, but this of course can be generalized to be a continuous variable, so you can think of it as a momentum. Let's say if you take a periodic boundary condition or some finite systems, or it can be in the end continuum limit, it can be like momentum, or it can be just a coordinate or whatever. Okay, so it's just for notational convenience use some discrete value and then particle number operators given by this. So the goal that what we want to do in the next two lectures is to derive a functional or field integral representation for the partition function. And let me just write down first the goal, and then I make a comment. Field integral representation for the grand canonical partition function. Trace of this operator here, and we won't write out the trace as a sum over complete set. N is a complete set of the Fock space. Complete set of Fock space states to represent the trace. Then beta is the Lewis temperature, of course, and mu is the chemical potential, which fixes the particle number. Chemical potential. So I mean, we have considered already this problem for a single particle problem. Now we are in the many-body context, so we allow for systems with flexible particle numbers. So the chemical potential is used as a Lagrange multiplier to fix the particle number, and I mean, temperature sets the energy. So this is the goal, to consider this partition function. So why are we interested in this partition function? Well, first of all, this will allow us then to look at all thermodynamic quantities. Okay, so from the partition function we can calculate thermodynamic quantities. So as said, so normally we are interested in open systems, so where the particle number is not fixed, and this is why we look at the grand canonical partition function. Actually, it's also easier to calculate than with the canonical. Now, there is, however, more to it, which I will probably, so now we are in the situation, so if I would have gone canonically, I would have first made a little bit a statement about imaginary time and real time correlation functions. But since you said I should like try to invert the order, I'm now trying, just giving the motivation, and then we'll see when we're going to make this connection, which I'm going to state now, more explicit. So what we saw is that the partition function in a way can be understood as a path integral, as a propagator, where you allow for imaginary times. Now the statement that I make here is we are interested in this object first because we can calculate thermodynamic quantities, and second is that we can introduce some sources, to this expression here, which then allow us by functional derivatives derive imaginary time ordered correlation functions. Okay? So you can think that this can be expressed as some path integral, and you can calculate like correlation functions which are then imaginary time ordered. Now there is a connection which allows us how to connect these imaginary time ordered correlation functions to those correlation functions that typically appear in transport calculations, like retarded and advanced correlation functions. Now this connection we have to see when we are going to discuss it, but it's not so relevant at the moment, because let's just take it as like a statement that this object is very interesting for us, because first we know about thermodynamics. Second, we can make a small modification, which I will state at the end, how to then be able to calculate imaginary time ordered correlation functions. And this you just have to believe me that there is some way how to generate from these all those correlation functions that we're interested in for like linear response transport. Okay. So this is the main goal. Now, how do we proceed? Or questions or clear? So this is, I mean, just take it as it is. So this is the trace. Here it's expanded in a complete set of Fox-based states. So we'll see how. Now, the idea now is just to use exactly what we saw before. So we can construct for this object some path or functional integral, okay? So, and this is the idea. So, again, what we want to do is we want to come up with some scheme where we, instead of looking here at operators, like can construct something that is then in one dimension higher, but allows us to substitute the operators for some C numbers, and then we end up with, I mean, the generalization of the path integral where we like extended dimension by 1, so we look at trajectories, not now of paths, but fields, and then in imaginary time, like we already have discussed, and this is then will be the representation that you're looking for. So let me just briefly recall the general construction recipe that we already encountered in the single particle quantum mechanics. So this is always like the recipe how to construct path integrals. Proceed in some like canonical steps, which are always the same. So, well, first, what we did in the quantum mechanics problem, well, we actually looked at the quantum mechanics problem, and then I think we didn't explicitly construct it, but just used the analogy for the statistic problem. But in the quantum mechanics problem, this was IT over H. And what we said is, well, let's divide this time evolution over the entire time into small time steps, and then make some approximation in the short time evolution, which will allow us to absorb the dynamical phase accumulated in a small time step into some dynamical phase by choosing an adequate state of a complete set of states, which are then, let's say, eigenstates of the approximated time evolution. So let's just do exactly the same. So here, let's now keep like the jargon and talk about like imaginary time evolution. Okay? So just because I think we are now familiar with this. So what we're looking at this here is actually a time evolution from, because it's a trace from, like in the statistic problem, from some point to another point, like this is point in top space, to another point. So we are looking at periodic path for a time evolution given by this imaginary time beta. So the idea is exactly again just to divide in the first step. Now here this imaginary time evolution in time beta of quantum Hamiltonian into infinitesimal time slices. And since I'm here discussing the general recipe, let's just maybe stay with really time, but you know how to translate this into the partition function we're talking about, where this would be beta. And in the end, we are actually interested in n to infinity. First, we make this for a finite time. So we start out from, let's say, this operator here. That's what we did, and then we form the product of n such terms. And factors. That was always the first step. Then the idea was that we can make some simplification in this small step Hamiltonian which will allow us to use some clever complete set of states, which allows us then to absorb the dynamical phase into just some number, accumulated just into some number by acting with these operators on some odd chosen states. So the idea is to absorb quantum dynamical phase accumulated during the short time propagation or time delta t into a set of good chosen or suitable chosen eigenstates. Okay, so this is always the same idea. So what we do is delta th over h bar, h bar. So we insert here some, let's say, resolution of unity. You can write as a sum over some projection onto field basis states. Now, in the single particle problem, what we did, so this step here was crucial to then make an approximation that we said, well, to order delta t, so in the single particle problem, this Hamilton operator consisted of typically a term which depended on momentum or on the coordinate. So we used that for, in the limit delta t to 0, we can write this exponential of the sum as a product of the two exponentials. And this then allowed to insert here complete sets of let's say, x or p states, okay? So now here we are in a situation where we want to make the same game, we want to play the same game, so we divide this into short times, we make some approximation, and we want to think what would be the adequate states to put in here to absorb then the dynamical phase accumulated. So I said in the single particle problem, well, we had the eigenstate of the x of the p operator. Now we are talking about the prototypical Hamiltonian, which we encounter in condensed matter, which is expressed in terms of creation and annihilation operators. So let's first ask like the question, what is a good choice for the many-variable Hamiltonian that I just have written down in terms of creation and annihilation operators? Well, and just by analogy, in the single particle problem, what we did here, well, we used the eigenstates of the x and of the p operator. Just by analogy, we would expect, well, it might be a good idea to look at the eigenstates of the annihilation and creation operators. So the answer, like the idea, we have to confirm if this makes sense or not, but just as an idea, well, the eigenstates of creation and annihilation operators look like a good option. So let's see if this makes sense. And this then leads us to the coherent states, okay? So that's the idea. Let's try to follow the program, and one essential step is to use a well-chosen states, a base of states to insert the resolution of units. So once we have figured this out, then we can return to the construction of the path integral. But first we should now talk about these candidates for states that should be convenient to construct the path integral. And now we should talk about, so this was all very general, but now let's first look at the problem of bosons, because they're more simpler, and then afterwards we look at the corresponding problem of fermions. Okay, so eigenstates of creation and annihilation operators. Let's first look at bosons. This leads us to coherent states. So I said here bosons. So let's start out from operators AI dagger, where I is again some discrete index taken from 1 to n. In the end, you can use a continuous variable, and where this is then from some interval, but for convenience, use some discrete set. So let these be bosonic Fock space operators. Fulfilling algebra. So this is now this commutation relations. And let's follow this idea that we said, well, for the construction of the many-body path integral, eigenstates of these operators should be very convenient. So the goal is search eigenstates of annihilation creation operator. So let's start with the second. So let's look if there's possible eigenstates of creation operators. Well, is it possible that you have eigenstates of an operator that creates, let's say, a state, a particle in state I? Well, the answer is actually, well, if you think about it, not really, no? Because, I mean, what you can do is you can write, let's say there exists an eigenstates of a creation operator. So this eigenstate you can write as a general Fock space state. So it should be a linear combination of some operators acting on the vacuum. So let me just write it. So assume that there is some eigenstate of a creation operator. Now, since phi itself is the state in Fock space, being a vector in Fock space, you can write it as a linear combination of some basis states. So it can be expanded in the following way. You can write it as some linear combination. Some indices ni1, ni2, and so on, and you have some coefficient n1, n2, and so on. And what you do is you act with the creation operator in state 1, state 2, and so on the vacuum. Okay, so this is here the vacuum state. Just write it down and explain it better. So this is a vacuum vector. Vacuum vector, and the Ci are just some complex numbers of their expansion coefficients. C and 1 and 2 and so on. Our complex numbers are the set of expansion coefficients. Expansion coefficients. So idea is if you have some Fock space vector, you can always write the state as starting out from the vacuum, which is destroyed by all the annihilation operators, so where you just don't have any particles, and then just putting in a given number of particles in state 1 and state 2 and so on. So you can create any state in the bosonic Fock space by just acting on the vacuum and creating then a given particle number, a given number of states. Now, a general state can be a linear combination containing different numbers of particles. So you can write a general state as just such a general linear combination where you have different particles created on top of the vacuum, and given each such, let's say, state with a given number of particles, some complex number. Okay, so this is just a very general state in the bosonic Fock space. Okay, that's clear. I mean, you're all familiar with this kind of notation, or so we're talking about Fock space, no, where you don't have any fixed number of particles. So this is just a general state. Now, if this indeed was an eigenstate of the creation operator, we can now see what happens. Well, if we act with this creation operator on the state, then we will just create one more particle in this one given state. Now, in this expansion here, actually, we can, so we have a linear combination of states with different particle numbers, but there will be one state with minimal number of particles, no? Let's say where just n1 is 1, or just n2 is 1, or actually can be also the vacuum can be in there. So there's a minimal, so there's in this linear combination, there's one state which has a minimal number of particles. Now if we act with this operator on the state, we will increase in all the states being formed here in the sum, we will increase just the number of particles by 1. So we will also increase the number of the minimal particles by 1. And then of course we see that this cannot be an eigenstate of the creation operator, because we end up with a different state just given the fact that the minimal number of particles, like in one of these states here, the linear combination is increased by 1. Okay, so we cannot have eigenstates of the creation operator. Okay, so just write this down. So if the minimal number of particles in phi, so if once in this linear combination there's one term which has a minimal number, if this is, let's call it n0, then the minimal number of particles in this, what we now assume to be an eigenstate, so this should be an eigenstate of this, so this should be again just some, if it was an eigenstate, it would reproduce itself apart from some eigenvalue, but now we see that the minimal number in this state is actually n0 plus 1, and this means that this cannot be an eigenstate of the creation operator, and actually we can never have eigenstates of creation operators. So creation operators AI operator cannot have eigenstates. Okay? So that didn't work out. Is the argument clear, or yeah? Okay, so this didn't work out, but still, I mean, we may think about the eigenstates of the annihilation operators. So maybe they may then serve as a good well-basis to construct a path integral. Well, is it that annihilation operators can have eigenstates? Well, we just see if we try to make this argument, then we see it doesn't really work out for the annihilation operator only. So we see that so if you would just try to apply the same argument for the annihilation operator, you could say, well, let's start out from some general linear combination, where now, well, the operator that we want to now find an eigenstate of this destructing particle. So let's try to use the same argument. A linear combination of states can be written in this way, and let's now call n0 the maximal number of particles around. So if you then act with the annihilation operator, you again diminish the number of maximal number of states, and it wouldn't be possible. But the great difference between the argument for the creation of annihilation operators is, well, we can start out from a linear combination containing an infinite number of particles. Okay, so if we just start out from a state which is a linear combination of infinite particles, well, then we see that we in a way break the symmetry. So then we can have eigenstates of the annihilation operator. Okay, and this leads to the coherent states, which you actually know from, I guess, from quantum mechanics. So let's first notice that the argument that we just used the argument, so for annihilation operators, AI, a similar problem, now similar meaning just trying to use the same argument by changing from a minimal to a maximal number of states does not arise. However, what we have to keep in mind that in order not to this problem not to rise, the eigenstates have to be really a linear combination of infinite numbers of particles. And in that, indeed, one can check that eigenstates of the annihilation operators can be expressed in the following way. So this is eigenstate. It's a linear combination of just infinite sum of creation operators. Okay, so this, I guess you know from when you discuss the harmonic oscillator, no? You find the eigenstates of the annihilation operators, which are the bosonic coherent states, and they are indeed linear combinations of this exponential function, which is an infinite sum. So you have an infinite number of particles, a linear combination of infinite numbers of particles. So where here, this phi just is a short notation for all the coefficients that parameterize this bosonic coherent state. Okay? So phi is characterized by n numbers, phi I, and they are the coefficients appearing in front of the creation operator in this exponential. So this is a set of complex numbers. So these states are eigenstates simultaneous eigenstates of all the annihilation operators, which means that taking any of these annihilation operators, AI, and acting on the state phi, you get this complex number phi I, and reproduce the state. And this holds for all I. Okay? So this should put into a box, to the box. These are the bosonic coherent states. They are simultaneous eigenstates of all the annihilation operators, and they should be convenient, these states should be convenient for the construction of our field integral for bosonic problem. Okay? So, are you familiar with bosonic coherent states, or? So, I think if I remember right, I had seen them in quantum mechanics, but when I heard quantum field, and then somehow it was completely, I couldn't really get the link. Somehow all appeared different. But I mean, again, it's good here then to play around a little bit with the coherent states. So actually, just the exercise to show that these are indeed eigenstates of all the annihilation operators, that's a good exercise. So I will just now write down a list of properties of the coherent states, some of which will be important for the construction of the path integral. And in the end of the lecture, I will just distribute an exercise sheet where you can try, or where you should try and sit down and prove the properties. But as said, so let's try to discuss this within the next 2 weeks. So you have like 2 weeks to go through the exercise, and then we should take one, instead of a lecture, take one day and discuss maybe these exercises. Okay? So this is just because it's good to work with these objects, because then somehow we get more feeling about them. So let me just write down some further properties apart from being eigenstates of the annihilation operators, further properties of bosonic coherent states. And of course, I mean, for the proof, for example, here, what you have to use, I mean, heavily is the algebra of the bosonic operators, no? So you have to think what happens. So, like here, I guess the idea is always to just expand, you see the series expansion of the exponential, and then see what happens if you commute the one annihilation operator that stands here to the side. And what you should see is, well, you get a lot of, okay, you have just to try to see that what will happen in the end is just that you will generate this number, this complex number parameterized corresponding creation operator. So, just further properties of bosonic coherent states. I think all of them, or most of them, are on the exercise sheet. If you don't have any idea how to do it, you can, I mean, always come to my room, and then we can just see if you can get some hints. So, just operating from the other side, no? The way the complex conjugate of the first relation. So this, I mean, it's just complex conjugate of the other one. Now you can ask, what happens if I act with instead of with an annihilation with a creation operator on a coherent state? And this is the result is given by this expression here. So if you instead of with an annihilation operate with a creation operator, you can show that this is the same as acting with the derivative with respect again to the corresponding complex number here on the state. Now there's one important property that we have to consider when we construct a path integral, and this is if you have two bosonic coherent states, each parameterized by n complex number, let's call them theta n, theta 1, theta 2, theta n, phi 1, phi 2, phi n, so this is always the short form for this n tuple of complex numbers. So let's consider two bosonic coherent states. Then you can look at their overlap. So at the matrix element theta phi. Well, if you normally talk about eigenstates of some operator, normally you would think, well, if these are eigenstates of operators with different eigenvalues, they should be orthogonal. But the coherent states actually not, they have a finite overlap. Okay? So this overlap between different coherent states is given by the exponential of this. Now, I think to be consistent, so let's just call this Overgas complex conjugation. Okay? I think I use it in the rest. This complex conjugation. Okay, so this is quite important, meaning that, well, let's call it first the overlap between coherent states, so it's not vanishing. Which means that the coherent states, that the coherent states are not pairwise orthogonal. Okay? So you have a finite overlap between different coherent states. And this, well, a trivial consequence of this is that if you look at the state with the overlap of a state with itself, then this gives you what is the norm of coherent state, which is the exponential. Of course, you could also start off from a normalized state, but as we wrote it, they have this norm of a coherent state. Coherent state. Okay, so this is one important property that we will have to have in mind when we construct the path integral using coherent states. So there we have a finite overlap between different coherent states. And another important property for the construction of the path integral is that the coherent states do not only form a complete set of states in Fock space, but an overcomplete set of states in Fock space. And I will say what I mean by this. So coherent states form an over complete set of states Fock space. So this is very important for our construction for the path integral, because what we said is we always divide the time evolution into small steps and then look at two factors and insert a resolution of unity in terms of states which allow us to accumulate like the phase into some number. So the choice of states will be the coherent states. So we need to have some representation of the Fock space unit operator in terms of the coherent state. And this is how it looks like. So you have a multiple integral. You have here complex integral with some normalization factor. Then you have here this exponential factor, which just takes into account that these states are not orthogonal, and then you have here the projection operators onto the coherent states. Okay, so this is the representation of the Fock space unit operator in terms of coherent states. Just the sum of projections, but it's like in the x spaces we could write an integral dx and then xx states. However, in contrast to the x spaces where two different ith states of the x operator would be orthogonal. Here we have a finite overlap between coherent states, meaning that the set of states of the coherent state forms a set of states in Fock space which is overcomplete, just given the fact that they are not pairwise orthogonal. Okay? And then one has to take into account this normalization factor. So this will be like the central identity that we will be using for the construction of the path integral. So, okay, well this will be the very important thing that we are going to use. Now, actually, okay, questions or?
In the second prepared, the right-handed side. No, here, the second prepared. Yes. This is a derivative, correct?
Oh yes. So I always use like a partial derivative. I always use like a short form.
Okay.
Yeah. Yes. So. Okay, so actually, like with this information, we could now start like trying to follow the general recipe that we wrote in the beginning to try to construct the path integral representation for the partition function of many-body bosonic problem. However, what we want to do is we want to construct the many-body path integral just in one form, just for bosons and fermions in one way. So what we have to now look at is at coherent states of the fermions. So once we have these, then we can just in a generalized way construct the path integral for the many-body Hamiltonians, just because it's identical apart from the slight differences between, important differences actually between coherent bosonic and fermionic states. But this is why we now turn to the fermionic coherent states already. Although we already have here all the information we need for the construction of the bosonic path integral. Maybe just make 5 minutes break and then we start.